My name is Melissa, and today we're going to look at how to teach computers to detect stem cells. We're going to start by considering these 6 patches taken from an MRI of a rat brain. This rat has been injected with stem cells. Can you tell the difference between the patches that are centered around a stem cell and the ones that are just centered around a dark spot? As we can see, this is a difficult task visually, and it turns out there is another reason that this is a challenge. In order to even obtain this data, trained professionals, often radiologists, have to carefully inspect each MRI scan to identify the stem cells. Afridi et al. Was able to compile just such a collection of 6 MRI scans. They also recorded the amount of time the experts took to label the stem cells, with the idea being that the longer he or she takes to label that stem cell, the less confident they are in that label. But not only are there many options when it comes to classifiers, we also have to find the appropriate parameters for that classifier. For instance, let's say we want to predict what color this black dot should be. We might choose the k-nearest neighbors classifier, but we also need to specify the number of neighbors to use. We can use 2 neighbors, in which case the dot would be predicted to be yellow. But if we use 5 neighbors, the prediction would be green. To find the right models for us, we use an automated machine learning tool, often referred to as AutoML. The tool we chose is ATM, which stands for Auto-Tuned Models. ATM produces several optimized classification models on just the MRI data, so we're not considering the labeling behavior data at all. And right away, we obtained 30 models that achieve comparable performance to Afridi's deep learning approach. But now that we have several optimized classification models, can we somehow join them together to push the performance even further? We leverage a technique known as score fusion to combine the models. What we consider as scores are the model's confidence in their prediction. For instance, in our k-nearest neighbor example, this spot is predicted to be green because 3 out of the 5 neighbors are green. However, the same KNN classifier model would have much higher confidence in predicting this dot as green, where 4 out of the 5 neighbors are green. And once we have a score for each of our models on all the MRI patches, we train an SVM to fuse the models together and produce a new prediction. And this approach gives us an AUC accuracy of well over 99%. Keep an eye out for the work presented here, along with this approach tested on other medical imaging datasets in this paper. And if you have any questions about this research, please email me at dalemelly@msu.edu.